And so, yeah, these are in the reference configuration. All right. Now, if you recall, our definition of P prime of S was rho 0 of S partial E, where E is a function of the deformation gradient of S and the local density of S with respect to Fs, right? So it's the tensor gradient at constant density. And I told you last time that this would be a really hard experiment to do, right? We have to go into the lab and somehow hold the density of the solid fixed in a porous material, and while computing, doing tests and computing stress-strain relationships, right? So what we're going to do now is, it's convenient to introduce what we're going to call the specific volume, and it's just simply 1 over the local density. Okay, so this is just for convenience. We're going to introduce this thing. And so now our internal energy of the solid, same as above, we could write as a function of the deformation gradient of S and the local density of S, right? Well, 1 over the local density, right? So if it's a function of the density, it's a function of 1 over the density, you understand? Right? So I can substitute in the specific volume for that term, right? Nothing really changes. All right, so let's compute using this definition. Let's compute the total differential of this energy. So we'll say ds is equal to partial es partial fij s d fij s plus partial e partial v s dv. All right. Now, we noted before that just through exercising the variational principle, computing those variations, that the Lagrange multiplier P turned out to be the thermodynamic pressure. Okay. And if we introduce our new definition of the specific volume as 1 over the density, then what we can show is that this what that equals is partial E S partial V S. And that's because this term, partial V bar partial rho bar S, right? V bar is 1 over the density, so we can compute that, right? And if you compute it, what you find out is that it's the negative density squared. Negative 1 over the density squared. So this term out front cancels, and you're left with a negative sign, which shows that P is equal to that. Okay? And who's heard of a Legendre transformation? So in mathematical physics or thermodynamics, you can use a Legendre transformation on it's basically, you know, if you've had what would you cover? Maybe an advanced fluids class or something. Typically, it's used as a way to transfer between the Gibbs free energy and the Helmholtz free energy, right? But you can think of it as just a way to basically switch the dependence between what we want to do now, because we've identified that P is, and what we'll see is that this is said to be conjugate to V, and therefore we want to basically shift the dependence of our energy term from V, which it is now, onto P, right? Let's just work through it. So what we're going to do is we're going to define a new energy functional we'll call E tilde, and it's a function of f of s and P. And what it's equal to is ES, which is a function of f of s and V of s, plus P V of s. Okay, this is what in mathematical physics would be called a Legendre transformation. P and V are said to be conjugate to each other. Okay, so let's compute the total differential of E tilde. So d E tilde is equal to d ES plus P dVs plus V dP. Now let's substitute in dE from above. Basically, we're going to substitute this here. So we get dE tilde S is equal to partial E partial Fij dFij plus partial ES partial V S dV bar S Now notice this thing is equal to minus P from up here, right? This equation. So that's minus P, so we have minus PdV plus PdV, so those terms cancel. And so we're left with dE tilde of S is equal to partial ES partial Fij dFij that thing. So then from this relationship, we can see that partial tilde partial S partial Fij. So basically, I'm going to divide this equation by Fij holding P fixed. Okay, and that gives me dE tilde Fij holding P fixed is equal to dES Fij holding V fixed, and partial E tilde partial P evaluated at holding Fij fixed is equal to V. So then I'm going to rearrange my Legendre transformation, just solve for E of S in terms of E tilde of S minus PV. And then I'm going to compute the derivative of this thing with respect to Fij holding P fixed. So just partial ES partial Fij S holding P fixed. Okay. Now I'm going to multiply this equation through by the reference density of the solid. I guess there's one thing here, yeah. Note, because of this relationship here, right, I can substitute that in there, and then I get partial E holding V fixed. Okay, all right. So we have a name for this thing. We called it P prime of S. It's the same, right? That's how we defined it originally. Even on this page, right? Right there. Holding P, understand, V bar is just 1 over rho bar. So if I hold P rho bar fixed, I hold V bar fixed. It's the same. So this thing we call P prime of S. Right? So what we'll do is we'll give this thing a new name. We'll call it P double prime of S. Right, so P double prime of S equals P prime of S minus P. I'm going to use, since we already have this definition that, well, I'll just say that the reference, using the same idea that this is 1 over V bar S, right? I'm sorry, not V bar, VO. 1 over VO of S, right? Same definition, just now in the reference density, okay? So then I have 1 over V0 partial V S partial Fij evaluated at constant P. So then I'm just going to solve for P prime of S. So I have that P prime of S, P prime S, is equal to P double prime of S I'm going to go ahead and I kind of mixed, this should be IJ, right? IJ. Okay, plus 1 over V0 partial VS partial partial Fij evaluated at constant P, right? But remember, we have that J of S from the conservation of mass, right? We have rho 0 bar S phi 0 S over rho S phi S, which is the same if we substitute in our definition for the specific volume, then we have V S phi 0 S V Okay, so from this, right, this is just conservation of mass, which we have been working with. And then I can substitute in my definition for specific volume, and I get this, right? Well, I could solve this equation for V bar of S as a function of J, right? So I won't do that, but it's clear that V bar of S is a function of J of S, right? That's clear. So with that, I can apply the chain rule to this term. So again, P prime of S is equal to P double prime of S plus P 1 over V0 partial V of S partial J S partial J S partial Fij comes to P. Well, we've seen this thing several times already, right? This is the partial derivative of the determinant of F with respect to F. Yeah.
In that del E till del P, when you're holding Fij constant.
Yep.
In that term, shouldn't it be like del E till S?
Here?
Yeah.
Yeah. Yeah, we're only dealing with the solid right now. Okay, so yeah, we've seen this term before, right? This is the partial derivative of the determinant of F with respect to F, right? And that thing equals J of S F J I, so the transpose inverse. Okay, so now we have an expression for P prime of S in terms of P double prime of S, and P double prime of S is something we can do an experiment on, right? It's the partial derivative of the internal energy with respect to Fij holding P fixed, right? Which includes P equal to 0, right? So you can go into the lab with your porous material and test the solid skeleton holding P fixed. P could be atmosphere, right? Holding P fixed, and then you can develop a constitutive model. So all you have to do is take your porous skeleton, go into the lab, and do a stress strain analysis on it, right? And now you have something. So P double prime of X is something we can do an experiment for, right? But we got this other term here, okay? Well, let's see what happens when we plug this back into our momentum equation, right? So now our momentum equation had P prime of S in it, right? Let's plug this back into the momentum equation. So we had 0 equals Now we're going to call this thing B. So we also have a boundary condition we could do the same thing for. We can also push that forward to the current configuration to get and the boundary condition where B is equal to 1 minus 1 over is Biot's coefficient. Biot's coefficient in a finite deformation setting. Okay, so this thing here, as we'll see in shortly, this is actually a material property, right? And this is something you could do in the lab, right? Remember, this thing is just 1 over the density, right? So we could go to the lab and we could monitor the density, say with like CT or something, right? CT imaging. We can monitor the density of the sample undergoing finite volume change, right? And if we do that, then we come up with a material property, holding P fixed, right? So again, P fixed includes P equals 0, so you could do this in an undrained sample in the laboratory. Right?
Professor,
Yeah.
Can you say that the Biot's coefficient is sort of a proxy for the amount of fluid in the pore?
No, it's right. This is on a solid, right? Biot's coefficient basically has to do with the density change of the solid, due to the fact that there's both pore pressure from the fluid and potentially external confining pressure, right? So basically the density of the solid, you can hold the confining pressure fixed and increase the pore pressure and you change the density of the solid, right?
So why do they generally keep it at 0.85 for Eton's equation?
We'll see that in just a second. Yeah. No one has ever